There is a branch of science, cosmology it's called, that concerns itself with the past, present, and future of the universe as a whole. How did that universe begin? How has it evolved? And where is it going? There is another branch of science, in the realm of physics to be exact, which is called mechanics. The science of mechanics concerns itself with something not quite as philosophical, perhaps, but no less profound. However it started, and wherever it's going, how does it all work? From the smallest particle to the largest cluster of galaxies, what keeps it all going? Whether it's speeding up, slowing down, changing direction, or cruising straight ahead, why does it all behave the way it does? Whether it's a solid, a liquid, or a gas, or an enigmatic unseen force, just how does it all interact? And why? All of these questions, from the simplest to the most profound, are by no means late arrivals. In one form or another, they've been around as long as there have been people to ask them. Even the earliest human inhabitants of this planet must have looked up at the sky and across the landscape and asked, how does it all work? And without even knowing it, they had taken the first tentative steps toward discovering and understanding the mechanical universe. If there is a key to understanding the mechanical universe, it can be found in the realm of mathematics. And among early civilizations, there were no greater mathematicians than the ancient Greeks. The work of Greek mathematicians added immeasurably to the advancement of science. In the area of circles, for example, they worked to the point of exhaustion, which is precisely what it took to find the number pi. But despite, or maybe because of, such brilliant discoveries, the Greeks fell behind. Once the Golden Age was over, they placed a lower value on the questions than on the answers. So, with too few questions, the world bought Aristotle's mechanics, with Plato's ideals, and eventually Ptolemy's solar system, in which the planets orbit the Earth uniformly, circles on perfect circles, was held aloft by conventional wisdom, answers instead of questions, that went almost unchallenged well into the Renaissance. The intellectual direction of Western civilization had fallen into line behind the endless circular argument of the Platonic ideal. The question isn't really why, unless it's why tamper with perfection. The question is how. How, 1,500 years after Ptolemy, was the perfect circle broken? And in what must seem another contradiction of logic, how did an orderly new world take shape in the crucible of scientific revolution? It began when an extremely curious Polish monk, Nicholas Copernicus, looked toward the stars and saw things in a different light. Among other things in the Copernican solar system, the Earth orbits the sun rather than the other way around. Why did Copernicus see the universe this way? And from a scientific point of view, how did such a vision make him the world's first revolutionary? An intellectual bridge that had spanned thousands of years waved precariously in the winds of change. Pillars of an age-old academic community were beset with threatening questions. No one was better equipped to fill the intellectual void than Galileo Galilei. Though Aristotelian thinking still ruled the world of the Italian Renaissance, Galileo was an exception to the rule. He was a Copernican with the courage of his convictions. In other words, he had the right idea at the wrong time. Fine, said his critics, an army which arose in defense of the status quo. But if the Earth really spins, why does a ball, dropped from a tower in Pisa, for example, land directly below? Why not in the next city-state? For a change, the answers were more dangerous than the questions. The Church, which considered him both a threat to Rome and an affront to common sense, warned him to leave things in their proper places. Nonetheless, in practice and theory, Galileo spoke the truth and proved what seemed to be the impossible. And when all was said and done,
well, in my left hand I have a feather, in my right hand a hammer. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
Galileo's findings are not only correct, they come down through history as an amazing example of the scientific imagination at work. With his brilliant mind set on explaining the universe in scientific terms, Galileo's experiments led him to discover the law of inertia. With uncanny physical insight, he accurately envisioned the parabolic path of projectiles, as well as the law of falling bodies. Even today, when they come right down to it, the questions behind these experiments are as challenging as they were 3 centuries ago. How did Galileo calculate a projectile's path? And by doing so, how did he begin to propel mathematics deeply into the future? In the days when seeing truly was believing, how did he disprove the obvious perception about falling objects? How can a hammer and a feather land at the same moment? And as Galileo himself fell from grace in 1633, why was the whole business of the universe a trial to everyone concerned? About the same time, every day was something of a trial to the wandering mathematician, Johannes Kepler. To a man in almost constant flight for his life, a life of illness and poverty, the loss of love and loved ones, witch hunts and the even meaner spirits of his associates, simple existence was something of a challenge. Surely, no man ever sacrificed more to grasp the scientific truth. But on the other hand, no man's discoveries ever proved more rewarding than Kepler's laws. The law of ellipses, the law of equal areas, and Kepler's third law of planetary motion, the law of harmony. With his laws of planetary motion as the key, Kepler entered the secret chamber of the cosmos. And yet, by explaining how rather than why the solar system works, he was destined to remain on the threshold of the mechanical universe. It was time for someone else to come along and take the final step. On this very path, which led directly to the moon, along came Isaac Newton with some crucial questions of his own. Why does an apple fall? Since an apple falls, why not the moon? If an apple and the moon fall for the same reason, why doesn't the moon, like the apple, crash into the earth? With such questions, the questions of a lifetime, Newton rather calmly sat down and piece by piece destroyed beyond repair the age-old machinery of the Aristotelian universe. And then, with answers that were equally astounding, he created something to take its place, the mechanical universe. The mechanical universe, a predictable, orderly universe, obeying precise mathematical laws. And with the laws of motion, the ability to take on almost any physical challenge. With his laws of motion, not unlike David confronting Goliath, Isaac Newton took on the great issues of mechanics. Armed with his keen mastery of forces, a precise knowledge of trajectories, and the universal law of gravitation. Newton mastered more than any human being before him, and for that, he deserves serious attention and considerable fanfare. Nonetheless, in science, answers are part of the past. The future belongs to the questions that science raises, which means that even Newton's laws were only a beginning in the right direction. For example, in modern times, a projectile can be guided with mathematical precision. How is that done? Part of the answer is an instrument called the gyroscope. How does it work? And in the all-encompassing mechanical universe, why is even a bicycle wheel a kind of gyroscope? Angular momentum is a key to the answer. But what is angular momentum? And why does it turn out to be so vital throughout the universe? From the cutting edge of the most distant galaxy to whirlpools in the family bath, angular momentum moves in all the best circles. And among other things, moving in circles is the key to keeping perfect time. Few things govern as steadily as today's mechanistic concern with time. However, while people now have more time on their hands, the preoccupation with it is hardly a recent phenomenon. What is comparatively recent, however, is the phenomenon of accurate time. It came about gradually, day in and day out, for 4,000 years. It finally arrived with an understanding of harmonic motion. What is harmonic motion? And when it comes right down and up to it, how does harmonic motion really work? And going full circle in the mechanical universe, how is it related to circular motion? The answer isn't as mysterious as it may seem at first perception, and there's no reason to approach it in a roundabout fashion. However, sometimes it helps. All it takes is a little differential calculus. While Isaac Newton's calculus goes far and wide throughout the mechanical universe, the scope of his generosity was considerably more narrow. Baron Wilhelm Gottfried von Leibniz strode the European landscape with the supreme confidence, and a number of good reasons for it. As a German diplomat and mathematician, Leibniz was so successful that Voltaire characterized him as the epitome of optimism. Worldly, outgoing, quite a fellow with the ladies, Leibniz had nothing in common with Newton, except the discovery of the calculus. There was plenty of room on Newton's plate for a little kindness. After all, he had created the laws of motion, the law of universal gravitation, the reflector telescope, a theoretical explanation for light and color. The menu of his unmatched accomplishments was extensive, to say the least. And yet, despite so much intelligence, Newton permitted, if not encouraged, a bitter controversy with Leibniz. This episode, only one of the emotional dramas in the mechanical universe, threatened the reputation of one man and the sanity of another. But it will also illustrate one of the curious paradoxes that lurk within the human heart of science. For example, while the scientist isn't always rational, the scientific environment nearly always is. In fact, a physics laboratory is where nature reveals herself in the most rational terms. Compared to Newton, what does the modern scientist really do? Beyond the well-intentioned textbook definition, what's the method of science? And in the real world, how does the scientific method really work? Sometimes it begins with a small beaker of oil, a sturdy iron pot, a dash of discipline, a measure of creativity, and perhaps a touch of genius. And sometimes, although very rarely, the result is as significant as the value of the charge of the electron. Who was this physicist? And by what painstaking means did he become one of the more famous men in scientific history? Past, present, and future, physicists are forever fascinated by the mysteries of nature. For example, the mysterious nature of light. Light. The very idea has been as hard to grasp as the almost incomprehensible vastness of the universe, and its speed has been even harder. Why does it have a specific value? Why is it called a fundamental constant? And precisely what is a fundamental constant of nature? And those who carry forward Newton's exploration perceive another operating principle of nature. Every bit of matter, everything from the outer edge of the most distant galaxy to the nucleus of an atom, is subject to 4 fundamental forces. In a complicated and confusing world, there are, or so it would seem, many different forces at play. Nonetheless, scientists have sought to reduce these to one, or at the most, to a very few. 2 fundamental forces dwell within the heart of the atom. Another knows no boundaries in the cosmos. And the fourth holds all matter together. The fundamental forces in the atomic nucleus are called the strong nuclear force and the weak nuclear force. The strong force binds protons and neutrons into nuclei. It's so powerful it can overcome the natural repulsion of protons. And this power can be released in nuclear reactions. Indirectly, the strong nuclear force sets fires deep within the sun and within other stars as well. And yet, as powerful as the strong force is, its range is so small that 12 zeros follow the decimal point to express it numerically as a fraction of a centimeter. The weak force, the other fundamental force within the nucleus, has effects that are by no means weak. Though its effects are subtle, they're very obvious. In the violent death of massive stars, for example, or in the decay of radioactive isotopes, a twist on alchemy that turns uranium into common lead. Increasingly, scientists are discovering how the nuclear forces link the past, the present, and the future of the universe. Yet, as much as is known about the strong nuclear force and the weak nuclear force, they remain somewhat mysterious. Hidden from the everyday world within the atomic nucleus, they remain among the innermost secrets of nature. The 2 other fundamental forces, equally wondrous and incredibly powerful, appear to be far less clandestine in nature, and they can be seen much closer to home. The most familiar fundamental force is gravity. Even in a commercial kitchen, the force of gravity accelerates mass. It came before both the chicken and the egg. But before Newton's law, people didn't know very much about gravity. They knew something about it, that it made things fall, for example, but they didn't know gravity makes the moon fall, nor that gravity, first and foremost, is a fundamental force of the universe. A fundamental force and an attractive force. As an attractive force, gravity can be described in popular human terms. Not only does gravity get around quite a bit, from one end of the universe to the other, it has considerable influence on everything under the moon. Far more than that, gravity relates to everyone and to everything. In a way, gravity reaches out and shakes hands with the entire universe. Another Englishman shares credit for advancing science closer to the moon. He was Henry Cavendish, and he actually weighed the Earth. Chemist as well as physicist, he isolated a gas that became known as hydrogen. Cavendish was as reclusive as he was brilliant. Most of his work was published almost a century after his death. Nonetheless, in his own quiet way, he weighed the Earth in 1798. He weighed the Earth by measuring the constant in Isaac Newton's universal law of gravity.
Force is mass times acceleration, expressed in kilogram meters per second squared, or newtons. From the acceleration of a falling body and Newton's law of gravity, Cavendish already knew the mass of the Earth times g. To isolate mass from gravity, he had to measure the value of g. This could be done by finding the force between two known masses, a known distance apart. It had to be done very carefully because the gravitational force between normal-sized masses is so very small. A bar, suspended by a delicate fiber, holds a mass at each end. Two larger masses are added. The gravitational force between these masses causes the bar to twist. By timing the swaying of the bar, he could deduce the stiffness of the fiber, and thus the force. Switching the masses around makes the bar twist in the opposite direction to correct for asymmetries in the experiment.
With this delicate experiment and a lot of care, Cavendish measured the gravitational constant and indirectly weighed the Earth. Weighing the Earth was an astounding accomplishment, but comparatively speaking, it's not truly shocking. The fourth fundamental force is electricity. Electricity seems the paradox of the forces. 1 minute exciting, raw, and even frightening in its power. The next, as ordinary as a pop-up toaster. On the bright side, electricity is as common as white bread. On the darker side, it conjures up images, some deadly, some mythical, and all of them somehow plugged into the character of Western culture. No image strikes closer to the American landscape than this Philadelphian harnessing electricity with a kite. Considering his unequaled accomplishments, editor and writer, inventor, politician, postmaster, and statesman, philosopher, the wit and wisdom of his era. Why has this image remained the most popular to this very day? Because Ben Franklin was young America's first and foremost scientist. In the course of studying its effects, Franklin had the ingenious but not quite accurate notion that electricity was a kind of fluid, an electrical fluid contained in each ordinary body. If the body held too much of the fluid, Franklin said it was positively charged with electricity. A body with too little was negatively charged. Franklin's terms, positive charge and negative charge, remain vital in the vocabulary of electricity. But the significance of the electrical force goes deeper than his reflections. At its most fundamental level, electricity is the force between positive and negative charges. It binds together everything in the universe, everything from soup to nuts, including the kitchen sink. Since that includes humans, why aren't they aware of the charges in their bodies? Why doesn't bread electrocute toasters? Every time people shake hands, why don't they fry each other like potatoes? Because everything has equal amounts of positive and negative charge for a perfectly balanced blend. Just as all matter is neutral, comprised of electrically balanced positive and negative charges, all matter is comprised of atoms. The atom's nucleus is made of protons, which are positively charged and illustrated in red, and neutrons in white, which have no charge. Negatively charged electrons, shown here in green, orbit the nucleus.
The electrical force is equal to the constant K sub E times the product of the charges, the Q's, divided by the square of the distance between them.
The formula for electricity is strikingly similar to the one for gravity. Gravitational force holds the 9 planets in orbit around the sun. The force is equal to minus a constant, G, times the product of the masses divided by the square of the distance between them. The natures of mass and charge are for the most part still unknown. But obviously mass is something that applies to gravity. Charge, something that applies to electricity. Since mass is always positive, gravity always attracts. Charge, however, can be either positive or negative. A positive and negative charge will attract. Two positive charges will repel, as will two negative charges. Otherwise, just as their formulas state symbolically, gravity and electricity are so much alike that an atom, with a little rearranging, looks almost like a little solar system. When scientists discovered that 2 of nature's 4 fundamental forces are almost the same, a logical question arose. Could there be one force that, alone, explained the fundamental nature of everything in the universe? Thus began the ongoing journey toward this single unified theory. And for the last 20 years of his life, Albert Einstein wheeled along this difficult path of research. Even though Einstein never reached his goal, the search continues and the findings suggest great promise. Found in the debris of nuclear collisions, these fragments suggest a deep underlying connection between the electric force and the weak nuclear force. Nevertheless, outside the realm of ongoing scientific research, the world of common experience continues to be governed by ordinary gravity and electricity. Gravity. It's the force that makes some objects fall, keeps others from spinning off the face of the earth. Gravity. It keeps the moon orbiting the earth and the planets orbiting the sun rather than wandering in space. Electricity. Just as gravity binds the planets to their appointed rounds, electricity binds atoms and molecules into liquids and solids that create everything from the most complex organisms to the most ordinary table salt. Although ordinary matter is electrically neutral, the atoms deep within can be both negatively and positively charged. Salt illustrates how these charges can hold matter together. Salt crystals are bound by the electric force between positively charged sodium and negatively charged chlorine ions. Electricity, in countless forms, is a fundamental force that constantly springs to life. For instance, the spring action of a metal object is actually an electrical process. Metal ions, which are positively charged, are glued together by electrons, which are negatively charged. Stretching the metal pulls the ions apart, but the electrons force them back together. Another form of the electrical force is friction. When two objects come into contact, their positive and negative charges interact, and their surfaces are, at least temporarily, bonded together. A third form of the electrical force is viscosity, which determines the rate at which fluids flow. For example, each of these beakers contains a fluid with a specific and different viscosity. The more viscous the fluid, the more slowly an object will fall through it. As with the actions of a metal spring and two objects creating friction, viscosity is a result of the electrical charges of their atoms. Here, as the objects make their way downward, liquid molecules flow around them under the influence of the electric force between them.